Good morning, everyone. So we had a lecture on black holes, and there was a chapter 1 with section 1.1, and so there is should be section 1.2, but there is no section 1.2. So we just continue to chapter 3. Well, actually 2. Chapter 3, which is about the Cauchy problem, so there is something called the Colombo rule that you have to know the culprit at the beginning of the episode. So the culprit here is the theorem of Schoekebuer and Geroch, and that's the spoiler. That's what I'm going to talk about. So this goes back to 62, maybe, or something like that. By the way, Ivan Schoekebuer will be 100 years in 3 months, mid-December, and so we will have a meeting to honor her here at ESI at about the time of her birthday. So if you're interested, you're welcome to join us. She's not well enough health-wise to participate, but she's still with us. And so the theorem says the following: given a vacuum initial data set, which consists of a manifold and some fields, and I'm going to explain what these fields are. And so this is we want to construct an n+1 dimensional spacetime. This is n-dimensional manifold, or sometimes maybe manifold with corners. So given a vacuum initial data set, there exists a unique up to isometries maximal globally hyperbolic development. So that's the theorem. This thing, I'm going to call it MGHD, so that I don't have to write the whole thing each time. Okay, so that's the key theorem of mathematical general relativity. It's like the fundamental theorem of analysis, fundamental theorem of algebra. Well, this is fundamental theorem of mathematical general relativity. Good. So you know already what globally hyperbolic means. Okay, so development, this would be a n+1 dimensional Lorentzian spacetime. So vacuum in this case, right? So I'm not going to repeat vacuum. Everything will be about vacuum here, so I'm not going to write it down. So development will be n+1 dimensional spacetime and an embedding of the data, right? Of the data to G. Okay, so that's development. Globally hyperbolic. Well, let me just remind you how this is. Globally hyperbolic, this means that for this purpose, you can think it as follows, right? That there exists a Cauchy surface. There exists a Cauchy surface. So that in this case, this is going to be sigma, so that every inextendable causal curve, inextendable causal curves intersects, which is intersected, right? So that is sigma, that's the same sigma as here in this case, causal intersects. Oh, I mean, this is called a Cauchy surface. So there exists a surface with this property that's called a Cauchy surface. Intersect sigma precisely once. So there is a variation of this definition where you just, instead of using causal, you're using time-like. And it doesn't change much. It changes a little bit. And it's more convenient for this setting. So I'm going to use, when sigma is going to be space-like, it's good, causal is good enough, but I'm going to allow for sigma which are not space-like, in which case you just need to take this definition as global hyperbolicity. It just doesn't change much in its properties. So that's the, good. So maximal, right? So maximal, then, so mg is maximal if it globally hyperbolic, if there is no isometric embedding of mg in a larger globally hyperbolic spacetime. Right? No isometric embedding into a larger globally hyperbolic spacetime. And so vacuum, you know what it is. Also, Ricci tensor is 0. Or could be actually proportional to the metric with a cosmological constant, but let's not worry about it. And well, I still have to tell you what an initial data set is. And that's going to be most of this lecture here. Yes, this is an equivalence theorem, right? So if this condition is satisfied, whether it's causal or time-like, then the diamonds are compact. It's part of this Geroch theorem, which tells you that globally hyperbolic is the same as having a time functions whose level sets are Cauchy surfaces. Right, so that's a beautiful, not trivial theorem. Well, once you know how to prove it, it's easy to prove, but you have to have the insight to do it. Good. So no, not necessarily. It just, yeah, you could, but it's not needed. Right, yeah. Good. And so this Kohn example, I'm going just to come back to it. So let's just put this in context first before I define what initial data are. But let's just at this moment think, so roughly speaking, at least the space-like data, they would be the metric and its time derivative on a space-like hypersurface, right? So I'm going to make this more precise, but let's see for illustration, roughly. So if sigma is space-like, so these are space-like Cauchy data. And I'm going to be more precise shortly. Then this would be the metric. And this would be a time derivative, okay, at sigma, right? Metric and sigma, and dt at sigma, whatever dt means. So the second order equation, Einstein equations are second order equations. So second order partial differential equation, the evolution problem needs as data the fields and their first derivatives. So for the moment, think about this like that, and let's do some examples. So we just take, R3 or Rn U as a hypersurface is Rn plus 1. And so tau T goes here. So we obviously have on this manifold a solution of Einstein equation, the Minkowski metric. What are the initial data here? Well, this would be the metric here, which the space part of this metric is just, so take this as T equals 0. And the space part of the metric, if I think of G mu nu as having indices going to 0, 1 to n, then the space part would be indices going from 1 to n, would be just the flat metric. The time derivative of the metric is 0. And the theorem says, well, given the flat metric here and 0 time derivative, there is a unique solution which goes with it, which is maximal globally hyperbolic and satisfies Einstein equations. That's the Minkowski metric. Okay, good. But so take the same Minkowski spacetime and remove a point here. Well, that's again a solution of Einstein equation. And the Cauchy data here haven't changed. So what about this uniqueness story? Well, of course, that's where this global hyperbolicity enters. Remember from two lectures ago, I mean, if you remove a point from Minkowski spacetime, then this is not globally hyperbolic anymore. Right? So because, as you said, there's this compactness of diamonds condition, which isn't apparent here, but is true. And if you just take a diamond around this point, then it's not compact anymore, right? So yes, you can remove a point from Minkowski spacetime. Yes, you get a solution. So you get a development, right? You get but it's not going to be globally hyperbolic. Good. What about this example? Well, you just take the Minkowski spacetime and you cut it. You just take for T between 1 and -1, right? So just take the Minkowski metric, but restrict time from -1 to -1. That's again a solution of Einstein equation. That's again the same Cauchy data. This thing is actually globally hyperbolic, but it's not maximal. Right? I can extend it to a larger manifold, which is globally hyperbolic. Right? Just Minkowski spacetime. It's globally hyperbolic. So this is a development, but it's not maximal. Right? So this global hyperbolicity means that you haven't missed some points in your spacetime. And maximal means that you've extended as much as you can, right? So and that's how you get uniqueness, right? Because of course, without, if I remove points, I'm not going to get the same manifold, so uniqueness will not work. And if I just cut a slab, then uniqueness will again not work because I can take a larger slab or even a larger slab and get different solutions. So that the key is this maximal globally hyperbolic thing here. And so somehow the spirit of the theorem says that, so morally, Einstein equations are predictable. In other words, you know what the universe does today, you'll be able to say what happens in the future, right? That's one way of thinking this. And that's a naive interpretation of the theorem because there's a catch. And let me show you an example. So we just take this metric, G is equal, very similar to something we've already seen before. G is equal minus, how was it? Minus 2 dt d phi plus, and the metric I showed you last time looked like that. So phi, so ER phi was in a circle, and there was a t-square here, okay? So this is a canonical example which shows that causality can go wrong with a metric. Well, this example has nothing to do with Einstein equations, but if you do this, then this is actually a flat metric. I hope I have it right. That if this is not flat, then there is a similar metric which is flat and has the same spirit. I think it's correct. So in other words, so you can think of this as well, 2 dimensions, and you've identified space into periodically, right? So rather than taking initial data on R, you take data on a circle. And so if you just take T equal, and let me change sign here. Oh, okay, let's leave it like that. So if you just think of data at T equal 1, so at T equal 1, the space part of the metric is G, phi phi is just 1 times d phi square. So it's just d phi square, so that's a flat metric on a circle. And obviously dt G is 0 here. So these are essentially Minkowskian data. So you have initial data for Einstein equations. And if I try to solve to the past from T equal 1, well, I can solve. Ivan-Shakebra tells me, good, I have initial data for Einstein equation, there exists maximal globally hyperbolic development. If I can, instead of solve to the future, nothing happens. But if I go backwards, I'm going to hit infinite time T equals 0. And T equals 0 is a null circle, right? So if I just take G of d phi at T equals 0, I get 0 because I'm taking the length of d phi, but there's a dt here, so this drops out. I get a T from here. At 0, it's 0. So this circle here, right? So this is from 0 to 2 pi, and I'm identifying 0 and 2 pi, is a closed causal curve. So how does it fit with the theorem? Well, Ivan and Bob tell you that, yes, there is a maximal globally hyperbolic development. This is this region. But actually, space-time doesn't stop here. Right? Space-time doesn't stop here. It continues here. And it continues in a pretty bad way. I mean, first you get this null closed curve. This surface, by the way, would be called a Cauchy horizon if you try to study this kind of effects. So that's the boundary of the globally hyperbolic region. You have a maximal globally hyperbolic region. Its boundary is actually called a Cauchy horizon. And then if you go beyond, if you go even further in time, right? So this length is G phi phi, is T, and it's negative if T is negative, right? Which means that the vector d phi is time-like here, right? So here you get a closed causal curve, a null one, and here each of these curves here is actually time-like. So you have a pretty bad causality violation, right? So the example we discussed a few lectures back, I had a t-square here. So this becoming time-like didn't happen. So t-square means that these circles are again space-like, but with this t, and the t is what makes it satisfy Einstein equations, is that you get time-like curves, right? So this is a problem, right? So Einstein equations are not predictable, at least for some Cauchy data, because they're telling you that, well, you have a solution, and it stops being globally hyperbolic, and then there is a region which is not globally hyperbolic. But then if I have this region which is not globally hyperbolic to start with, what prevents me to remove points here? Right? In the globally hyperbolic case, I had a good criterion why I shouldn't remove them, because it will stop the solution being globally hyperbolic. But once we are in this region, there's no good condition beyond the Cauchy horizon, which would guarantee uniqueness of the solution beyond the Cauchy horizon. And predictability is about having unique solutions, right? So one way out of it is the something called the strong cosmic censorship conjecture. Yes? Exactly. Right? So this is T larger than 0. That's the solution from the Schoeppe-Bra-Geroch theorem, right? So this is a strong cosmic censorship conjecture. Which is that for generic initial data, things like that don't happen, right? So, and this is something suggested by Penrose, and say, let's mathematical version would be, so for generic and say asymptotically flat initial data, I'm just going to comment on this asymptotically flat initial data. The maximal globally hyperbolic development is inextendable. Extendable as a Lorentzian manifold. So in other words, okay, there exists initial data where this happens. This is an example, but this is very special. Right? So physics is about generic situations. We're never in a very special case, all kind of fluctuations of fields around us. So we're going to never hit a case where we form Cauchy horizons. And so generically, so if we don't hit such a case, then, well, you should have uniqueness, right? So, of course, this is a conjecture. And there's one case where it has been, well, it has been proven in a few cases, but so let me, very special cases, right? Small data results, there are small data results, and there are also data results with symmetry. But it's just open, except for some small data results. But before I describe you these results, I have to tell you what the data are, right? So small data results. And some results with symmetry. Actually, in fact, U1 times U1, to be specific. Good. So, well, that's the conjecture, that's the setting, that's the theorem, and so now let's try to make this initial data precise. Now, there are essentially two settings. One is the characteristic Cauchy problem, and the other one is the space-like Cauchy problem. So the characteristic, you can actually do it in two cases. One is initial data on a light cone, and the other one is two hypersurfaces which intersect transversally. So, right? So if you see it sideways, that's what it looks like, and then these two surfaces which intersect. So I can't draw it, but that's the picture, right? So you have two hypersurfaces, codimension 1, which intersect transversally. And space-like is just this kind of picture to have in mind. And so let me start with characteristic because it's much easier. The characteristic, well, let's start with the wave equation, Laplace phi equals 0. And in Minkowski spacetime, so say you give data at t equal t minus x equals 0 and t plus x equals 0. So that's, and in Minkowski, how do you solve this problem? So this is two-dimensional, but again, you can just think of this in higher dimensions. So you could have just y and x, y2 and yn, right? So the other direction. So so how you solve this, you just give phi at t plus x equals 0. Then you give a function phi, say, minus. So this is a function on this surface. You give a function on that surface, phi plus is phi at t plus x. Do I have them right? Yeah, this one is t minus x equals 0. And you get a solution. Yeah, there exists a unique solution. And in dimension 1 plus 1, these are formula that you know just for the two-dimensional wave equations. Yeah, just to write explicitly the formula here, but it's true in all dimensions. So somehow this characteristic Cauchy problem is funny because you think of second-order equation, you should have the function and its derivative. But here you only need the function. That's how this works. And so how does this generalize to this equation in any metric? The same thing, except that this surface is now, so let's call this sigma minus and sigma plus. Then in this case, sigma minus and sigma plus are characteristic, which means the following, that the buzzword is the normal is tangent, right? So that's one way of understanding this. The normal to the surface is actually tangent to the surface. But another way of saying this, the definition would be that if you take this metric G, you pull it back, so I star sigma minus of G, you get a tensor field on this surface, and the tensor field has a signature 0 plus plus plus, signature 0 plus plus plus. Okay, so if you're not familiar with this kind of behavior, think about this example here. So let's take the Minkowski metric. So this is minus d theta squared plus dx squared plus dy squared. And we look at the surface t equal x. Right? So then the pullback of the metric is so sigma or plus minus. Is it my notation? It's probably actually minus plus. In this picture, then, well, if I take the pullback of the metric, so pullback of on sigma plus minus of eta, well, dt is, I can parameterize it by x, and then, but then dt is plus minus dx. So this cancels out, right? So this is dy squared. So this is this thing is if I'm in dimension n plus 1, right? So let's see. So if they are in dimension n plus 1, then these things are dimension n. But this metric has only, so this is the y's are go from to n minus 1, right? Because you have already one space coordinate here one time, so these go to minus n, right? So this has signature 0 and plus, right? So x is a coordinate on this surface, but the metric doesn't see it. So that's a characteristic hypersurface. And so good. So that's the definition of a hyperactistic hypersurface in a curved space-time. And then the theorem is the same. So given any, I'm not going to write it down, but just say it in words that given any data on these hypersurfaces, you get a unique solution of the wave equation. Right, so you give initial data on these two hypersurfaces, just the field, the value of the field, a tensor field, scalar field, wave equation, you get a unique solution in the future. And if your space-time is, if this is a Cauchy surface for the future, right, so you don't care what happens to the past, and actually there's a good reason that you don't care what happens to the past, because this problem doesn't tell you what the solution to the past is, right? So here, the space-like Cauchy problem, when you're giving data on a space-like surface, you can solve both to the future and the past. Here, you can only solve to the future. The data here don't tell you what happens in the past. But then, if this region is globally hyperbolic, then you get a unique solution, globally defined. Good. So what about Einstein equations? Well, that's the theorem which does that. And that's a bit more complicated. So let's go look at the characteristic case. So what would be the data here? Vacuum data. Is this induced tensor on each surface. Okay, so I'm writing induced tensor because it's not a metric. So what does it mean? Suppose you had a space-time, right? Suppose you had a space-time really, you can solve the problem, then you would get a metric in your space-time. And this metric would induce the metric, a tensor of on your hypersurface. And this, because this surface is supposed to be characteristic, this tensor would have signature 0 plus plus plus. And so the vacuum data would be this tensor, right? So you have a tensor, and what does this tensor do? Well, this tensor has a signature 0 plus plus plus, which means that it has a unique degeneracy direction, right? So there exists a unique degeneracy direction. Okay, so if you use coordinates, say r and some coordinates theta a on the surface, there exist coordinates on the surface, local, say, on sigma plus minus, so that the induced metric, well, this tensor field, which is not a metric, but it's going to look like, should I call it G? Let me call it G sigma, right? So G sigma, but it's not a metric. It has 0 times dr square, plus 0 times dr dxa, plus GAB dxa dxb. And this is now a Riemannian metric. So this is a Riemannian metric. So there's the degeneracy direction in these coordinates are adapted to this degeneracy direction. So in other words, dr is in the kernel of this metric, right? So G of dr is 0. Of this not metric. I'll be calling it metric. I apologize for this, but somehow it's just a simpler way. Good. So now, it's almost it, except there's a catch. There's something called the Ricciarduri equation. Now, this Ricciarduri equation, it has 2 versions. And this is the null equation. There's a time-lag version, which I'm not going to discuss. Null equation, which says that this component of the Riemann metric, of the Riemann tensor, is a function of only of this metric G, its first derivatives, drg, and a field kappa, which I'm going to define shortly, which says that some objects here are not free, but they have to satisfy. If you want to satisfy this to be 0, then this initial data has to satisfy this Riemann-Duris equation. What is this Riemann-Duris equation? Well, it defines something which is called the expansion of the surface. Let me drop this index now, just sigma of sigma. This would be just, this is a Riemannian metric. Well, actually, it's a family of metrics, right? Because it depends upon the R parameter and this. So you take the derivative, and take its trace. So this is theta, and I think that the standard normalization is 1/2. And this object is telling you essentially this is probably 1 over that GIB, dr square root that GIB. No, it's, let's go. I think it's correct, right? Yeah. Okay. That's the formula. So what is this? That GAB is the local surface area in these coordinates. Okay? So the determinant of this surface area is telling you how the area changes if you move along generators, right? So if this is positive, it means that the area, if you just take these no lines here, well, which are called generators. So you move along these lines, and you take a little surface here. This is telling you how the surface changes. Theta positive means that it expands, right? And theta negative means that it contracts. So this is theta, and then there is a shear tensor. And so this is essentially how the whole metric changes, but you remove its trace, right? So remove this trace. And so now I have to figure out the coefficients here, but minus theta GAB. Probably 2 over n minus 2 or something like that. So that it's trace-free part of, and please correct me if I have this coefficient wrong, trace-free part, but some numerical contribution. So you have to make sure that this has 0 trace, so remove its trace, and that's probably is my conventions. It's probably correct, keeping in mind that this is n minus, should be n minus 1. Okay. So, yeah. So this is an n-dimensional surface. This is n minus 1 dimensional. So I think that's minus 1. Okay, trace-free part of drGAB. So this is telling you how this metric changes when you move along these generators of the surface. And the Riemann-Duris equation is a very simple equation, which is just an identity. Take Einstein equations, write a metric which has a no surface, go through some painful calculation, and you're going to get this Riemann-Duris equation. So the equation is that RRR is maybe a minus, I think, well, let's just up to sign. It's dr theta plus kappa over, plus kappa, minus kappa theta plus theta square over n minus 1 or something like that, plus sigma square equals 0. So that, well, it's 0 in vacuum, right? So that would be the Piotr equation. So it's telling you that, well, there is a, if you give this induced metric or induced tensor field here, and then, well, out of this you can calculate all these things, and there is an equation which is satisfied by this object, where kappa is actually the connection along the integral curves of this node vector at the generators. Okay? In other words, you think about this as follows. If you have a one-dimensional manifold, in which case this is parameterized by R, then you have a vector field dr along this manifold. Then if you have a vector field along this manifold, then you can write it as one function multiplying the basis vector. And now if you want to differentiate this vector, then that's going to be a formula which you all know and love. One-dimensional connection, Christoffel symbols, so gamma r, 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 xr. Okay? So that's the connection of a one-dimensional manifold. So you have these degeneracy curves of this metric, and each of them carries this connection, and so this is this kappa. Right? Of course, this is a connection coefficient, so you can make it 0 by a coordinate transformation. So in other words, there exists a reparametrization of these curves here, so that kappa will be 0, and then definitely in this parametrization, this is an obvious constraint, right, on the geometry. So, but of course, a priori, you don't know what this connection is. So the characteristic data are would be this metric here plus kappa, right? So G sigma and kappa, and subject to Piotr equation, there's a constraint, plus constraint, which is only this one. That's all there is, Piotr equation. Right. Sigma is a characteristic hypersurface, right? So I had two of them, sigma plus and sigma minus, and on each of them I have this induced tensor field, which I call metric, but it's not a metric because it's a degenerate. So it has a degeneracy space. This degeneracy space carries a connection, and I have this induced family of metric of tensor fields, right? So each of them is a Riemannian. At each R, this is a Riemannian metric on the level on the level sets, right? So if you think about a light cone, right, that's a nice picture, then this would be the Riemannian metric on each set, and there will be this connection, and so that's all the data they are. And this constraint, well, if you go to a gauge where kappa is 0, then this is obviously a constraint on the metric G sigma. On the other hand, if you start with initial data for which dr theta has no zeros, then you can actually, let's see, I wrote it wrong, right? No, well, theta has no zeros, sorry. Theta has no zeros, right? So if you calculate, you give yourself a metric G, you calculate your theta. If theta has no zeros, this is an algebra. You can calculate kappa from the equation, right? So kappa is 1 over theta and dr theta plus theta squared. So that's a nice picture, because for such surfaces, you don't have a constraint, right? In other words, this kappa becomes an algebraic field, which can be determined from the G's. So it really becomes a constraint if you have a region where there are zeros, and then you have to worry about smoothness there. In odd region where theta is not zero, you can just algebraically determine this. So this is the initial data, and well, the Schokebrua-Garroch theorem tells you that for such data onto hypersurfaces, you get a unique solution of Einstein equations to the future. Unique, maximal, globally hyperbolic up to diffeomorphism. So this is the characteristic Cauchy problem on Einstein equations. Well, what about the space-like one? Well, the space-like one, I have 2 minutes for it, right? So let me just do the space-like one very quickly. Space-like one, so the initial data will be morally is a manifold, a metric, and its time derivative. And more precisely, what you need is sigma is still okay. G would be the induced metric, induced Riemannian metric. And well, what is the induced Riemannian metric? But if you want to construct, if you have your metric at the end, the final metric has be such that its induced metric is this, okay? So that's what it means, right? So you start with a some Riemannian metric, and in the development, it's going to become the metric induced on this hypersurface, like this. And here, G actually use K, which is the second fundamental form, or in some terminology, or extrinsic curvature tensor for in physicists, that's what they call, what they will tell you. And it really measures how the metric changes if you start moving transversally to the surface. And there's a catch that if you look at the vacuum Einstein equations and you contract them with the normal to your surface, right? So suppose you have your surface here, and you can find a solution, then it's embedded in a larger space-time, then there is a normal field here. Of course, if you start with your initial data, you don't have a normal. You just have this surface. But once you've solved it, then you would have a normal. And if you look at these equations, there's something called the Kodadzi-Menardi-Gauss embedding equations. Menardi-Gauss embedding equations. Which tell you that you can calculate this part of the Riemann tensor just out of these fields. Right? So in other words, R mu nu are second order operators. So you need normally 2 derivatives of the metric to calculate R mu nu. But here, this part of the equations, you only need, well, you need two derivatives in space directions, but you don't need 2 time derivatives to calculate them. Right? So that's the point. You don't need two times derivatives. And so these equations are something called the vacuum constraint equation. The Ricci scalar of the metric G is the norm of K square minus the norm minus trace K square. And the divergence of this tensor Kij minus K Bij is 0. Okay. So these are intrinsic equations for the metric G and this second fundamental tensor field, and they have to be satisfied as a necessary condition to get a solution, right? Because if you want an R mu n equals 0, it better be that this is true, and then therefore your initial data G and K are not arbitrary. They have to satisfy. This is called the scalar constraint equation. This is called the vector constraint equation. And so the theorem by Ivan and Schokebrua, by Ivan and Bob Garroch tells you that you give such initial data, you get a unique solution of Einstein equations, which realizes this data. Let me just the last comment, say that it's really an amazing theorem because you don't need any asymptotic conditions or any completeness or anything like that, right? So you get anything, you give any Riemannian manifold, it can have Rho, it can have any topology, it doesn't matter. You get a solution. Right? Now, you get a solution which is globally hyperbolic, which is maximal globally hyperbolic. It can have horizons, and then that's one of the key mathematical problems, understanding formation of Cauchy horizons when you evolve things with Einstein equations, and I think my time is over, so open for questions.